Hey everyone, we're now going to use Zoom to test its capabilities. Here we go, homework on central limit theorem. Let's go to the book. Your first problem was page 287, number 5, and then number 8. So let's read number 5 and number 8. Here it is. Hot dog. It says in exercises 5 through 8, assume that women's heights are normally distributed with a mean of 63.6 inches and a standard deviation of 2.5 inches. 5A says if one woman is selected, find the probability that her height is less than 64 inches. And part B says if 36 women are randomly selected, same question. So let's go back to the homework. Let's see if we can do this. There we go. Great. All right, so for 5A, I put 63.6 inches right in the center. And I put 64 right here. So to find this z-score of 1.16 for part A at least, I took the 64 minus 63.6 and I divided by the standard deviation of the population, which is 2.5. Why did I do that? And that's how I got 0.16 as a z-score. Why did I not apply the central limit theorem? Because for 5A, I'm only sampling one woman. The central limit theorem does not apply or kick in until the sample size is greater than 30 people. Taking us to part B, now we're sampling 36 people in part B. So the central limit theorem now applies, it kicks in. That's why I don't use the standard deviation of 2.5. That's why I use the standard error of 2.5 divided by root 36. So to find the z-score here, I did 64 minus 63.6. That doesn't change. But now I divide by the standard error of 0.417. That's what gave me the z-score of 0.96, which I used right here. So then 0.16 gives me an area of 0.0636, add it to 0.5, and that's how I get my final answer. And same thing here. A z-score of 0.96 gives me an area of 0.3315. Add that to 0.5, and I get my area of 0.8315. So, same question. The difference is sampling one person versus sampling greater than 30 people. That's when the central limit theorem kicks in. Number 8. Let's go back to the book. Let's go to share. Let's go back to the book here. Let's see if this works out. Number 8 says, if one woman is selected, find that her height is between 60 and 65 inches. And part B says, if 16 women are randomly selected. Now there's one kicker here, 16 women, definitely less than 30. But I want you to go back to blue here. It says, assume that women's heights are normally distributed. The corollary to the central limit theorem states that if you take a sample size less than 30, but the distribution of the population is already normal, then you can violate the greater than 30 stipulation. So let's go back to the homework. All right, so for part A, let's see, one woman again, I divided by the standard deviation of 2.5. That gave me z-scores of 0.56 and negative 1.44 respectively. That gave me areas of 0.4251 and 0.2123. I added them together and got my answer. Here, I needed to find my standard error. Even though my sample size was less than 30, I still found the standard error of 0.625. I divided by 0.625 now, and I got z-scores of 2.24 and negative 5.76, off the charts, yo. And because negative 5.76 is off the z-table, I use a z-score area of 0.4999. Remember that? Plus the area out to 2.24, which is 0.4875. And I get my answer of 0.9874. Okay. And part C asks, why were we able to apply the central limit theorem even though the sample size was less than 30? And the answer was what we stated, because the original distribution, the population, was already normally distributed. All right, moving along to numbers 10, 11, and 14b. Let's go back to the book. Let's read number 10. Number 10 states, that the new Lucky Lady Casino wants to increase revenue by providing buses that can transport gamblers from other cities. Research shows that these gamblers tend to be older, they tend to play slot machines only, and have losses with a mean of $182 and a standard deviation of $105. The buses carry 35 gamblers per trip. The casino actually gives each bus passenger $50 worth of vouchers. So the casino needs to recover that lost cost, that lost money, in order to make a profit. Find the probability that if a bus is filled with 35 passengers, the mean amount lost by a passenger will exceed $50. I don't know if you realize this, but this is very real. My grandmother used to take these buses all the time from Pennsylvania to Atlantic City, and they would give them free cash. That's a real thing. So basically, in order to make the money back, each person has to lose more than $50, aka the money they were given. People on average lose $182. So 50 is way over here to the left. So let's find this line right here. What would be the z-score of 50? First, you got to find the standard error. You take the standard deviation of 105, divide by the square root of the 35 passengers, and get 17.748. I will calculate the z-score one more time here. It will be z equals 50 minus 182 divided by the standard error of 17.748. This is just a z-score question, everybody. And that gives me a super duper low z-score, negative 7.44, way off the charts. So I take the area associated with that, which is 0.4999. I add that with 0.5, and I get a whopping answer of 0.9999. Basically, even though people are gambling, the casino is not gambling. They are essentially guaranteed nearly 100%, 0.9999 chance that they're going to make their money back and make a profit. So it's a pretty profitable venture. All right. 11, same thing, way off the charts. 14B, way off the charts. If you have questions with those, please email me personally. Let me get to 21 and 22 to finish up this homework right here, because this might be where you had your issue. 21A, let me get to the book. Okay, 21A said, what did it say? Let's find out. You need to build a bench that will seat 18 male college football players, and you must first determine the length of the bench. Men have hip breadths, which is basically a width, that are normally distributed with a mean of 14.4 inches and a standard deviation of 1 inch. What is the minimum length of the bench if you want a 0.975 probability that it will fit the combined hip breadths of 18 randomly selected men? A lot of things going on here, so let's unpack it. All right, back to this. So I want a 0.975 probability that I'm going to fit everybody. So where would I draw a line so that 0.975 would go to the left? That's what you need to think about for this problem. That line would be way over here to the right, wouldn't it? So think about that right now. To the left of this line would be 0.975. But if I break that 0.975 down, I obviously get 0.5 to the left of this center line right here, which leaves 0.4750 if you think about it. So one thing I need to look up backwards. This is one of those backwards looking up problems on a Z table. Let's see if this works or not. I'm going to try to go to my Z table. I don't know if it will, but I will. So where is the closest Z-score to 0.4750? I'm going to look that up right now. 0.4750, I see it right here, actually. It's exact. It's 1.9 and then over to 0.06. So the Z-score that's closest to that is 1.96. All right, hopefully you saw the Z table like I did. I'm not sure if you did or not. Okay, so now this is a finding scores backwards question like we had on test number 2. I take the Z-score formula, x minus mu over sigma, and I solve it for x. X equals mu plus z times sigma. That's what I did right here. And so I did 14.4 plus 1.96 times the 0.236, which is the standard error, 1 divided by root 18. Why can I use the central limit theorem here? Because men's hip breadths are normally distributed. And I get a hip breadth of 14.86 inches. And that would be the answer. But remember, we need 18 football players to sit on this bench. That's the hip breadth of one football player. So I need to take that 14.86 and I need to multiply by the 18 football players. And that's how I get my final answer of 267.48 inches. Now listen, that's the answer to this question, but that's not necessarily accurate, because if you really think about it, in order to fit football players on the bench, their shoulder pads are the widest part. Unless they're sitting like this, it's not that realistic. Yeah, there's my video. Let me take myself off right there. Okay, last one I'm going to go over is number 22. And 22, let's go to the book. Last problem. It says the Boston Women's Club needs an elevator limited to 8 passengers. There's 120 women members with weights that are approximately 143 and a standard deviation to 29 pounds. Part B says, we want a 99% probability that the elevator will not be overloaded with 8 members. What should be the maximum allowable weight? All right, let's get to this last question right here for A and B. All right, so the first question that we ask is this. Well, actually, let me go backwards to part A. I apologize. Let me go back to part A. If 8 different members were randomly selected, find the probability that their total weight will not exceed a maximum capacity of 1,300 pounds. There's something unique about this problem. The unique thing is that this is a finite population, 120 members, and we're sampling without replacement, because once a woman is on the elevator, she can't get on the elevator again. So because of that particular situation, I had to do the finite correction factor test. I had to see if little n was greater than 5% of capital N. In other words, is 8 women greater than 5% of 120? The answer is yes. It is. Oops. Yes, yes, yes. So we're using the finite correction factor. So to find the standard error, I take the 29 divided by the square root of 8, but then times the extra square root piece, everybody. Keep that in mind. That's how I get my standard error of 9.947. Some of you are not rounding standard deviations to 3 decimal places. Make sure you do. Okay, so got the standard error. I found the z-score of 162.5, which just coincidentally gave me a z-score of 1.96. That gives me an area of 0.4750. Add it with 0.5, and I get an answer of 0.9750. Question, Mr. Clody, where'd you get 162.5 from? It said the total weight of the women is 1,300 pounds. So then you have to divide that by the 8 women who are on the elevator. 1,300 divided by 8 averages out to 162.5 pounds. I did skip that part. Okay, last but not least, now I want a 99% probability. So this adds add up to 99%, which it breaks down to 0.5 and 0.4900. And if I look up my z-table backwards, the closest z-score to 0.4900 is 2.33. So then I apply the z-score formula backwards, and I get an average weight of 166.18 pounds, LBS. But remember, there's 8 women on the elevator, so I take 166.18, multiply it by 8. And if I want to be 99% sure that I don't overload the elevator, the weight cannot exceed 1,329 pounds. Hope this was helpful. Bye, everybody.